Hello there. Today we are talking about bugs of shared state. In the previous talk, we talked about code rot, code smells, and common software defects. And I mentioned that there are stateful code smells and that three groups of smells stand out in particular. And today's talk is about bugs of shared state. Basically, one of the coolest things that computers can do is duplicate data with ease. Cloning large swaths of information and shifting state in a system running trillions of times a second with only the latent forces of molecular chemistry pushing back on the physics of calculations is pretty freaking sweet. It may sometimes seem that the capacity of a computer is infinite and anything is conceivable and instantly available. But as anyone who has ever attempted to copy multiple seasons of Gilmore Girls onto a flash drive soon learns, that's false. The relativity of time and space still applies in software and hardware, and this puts limits on the code that we write. And what makes shared state bugs so heinous and much worse than mutated and unstructured state bugs is that there are fewer measures to prevent these defects. Yeah, functional programming can help avoid mutated state bugs, and type languages can limit the extent of unstructured state bugs. But many shared state software defects have their roots in mathematics, logic, and physics, and not only cannot be fully prevented, but can also manifest themselves outside of software in economics, business, and society. JavaScript, Python, and Ruby, these are all interpreted languages that will run from a separate executable runtime that will compose abstract syntax trees of your code to be executed just in time. And this means that the code has to be compiled, interpreted, and run all at once. And so the performance of this software comes with a small overhead. In other programming languages, we'll use software pre-compiled into something close to bytecode that then a virtual machine can execute on its own. And the overhead is still there, but it's paid at compile time, and the software is fast. But languages like C and C++, Go, and Rust will all compile into executables that can run natively for an architecture. Software built at this level is highly sensitive to the hardware, operating system, the capacity of the executing machine. And many of the defects I will talk about today lurk in this low-level realm of software. And special shout out to Rust as a language that has structured itself with a compiler armed with functional programming, and a strictly typed language that has proven itself to be the most recognizable, secure, and NSA-blessed language for building mission-critical, memory-safe software. But even programming in Rust, a developer can find themselves facing shared state defects such as race conditions. Race conditions are problems of ordering of asynchronous processes in the system. And as a result, these bugs are inherently common in multi-threaded or distributed software environments. And there are quite a few wacky racers. One specific type of race condition is deadlocking, where two resources find themselves depending on each other in order to proceed further. State needed by one thread may be held by another, locking code execution in a catch-22 of lameness. You might have experienced this yourself when trying to step aside for someone in a narrow doorway, only to get in the way of their courtesy again and again. And in humans, this phenomenon is known as a Canadian standoff, where threads are too polite to do their job, failing to execute and win. This is in contrast to a Mexican standoff, which is a situation in which no one can emerge as a clear victor, and where parties are too eager to execute and lose. In software, this situation is called a live lock, and there is not a general solution to preventing deadlocking or live locking within a program. In fact, such a solution would suggest there is even a solution to the halting problem, a paradox of computability and logic. Race conditions in critical systems can lead to non-determinism and even data corruption, which are horrible messes to clean up. Another kind of race condition is resource contention. This is like deadlocking, but with far more actors vying for fewer resources than available. This usually occurs not because the resources are too few, but because uncoordinated demand is too high. Bad code can prevent shared resources from being returned. And in a computing context, this has traditionally been memory constraints. But in software, this could also be things like file handles, and port allocations, and swap space. There is only so much that can happen at once. Humans will call this phenomenon the tragedy of the commons. It will happen when you're grazing too much cattle, or from overfishing, or from any actions by people that ultimately becomes unsustainable without coordination. This is resource contention. Memory leaks are remnants of allocations on the heap, unfreed by the program, and left unattended, they can become threats to the whole system. Memory management in C and poor considerations of file operations can cause these. And thankfully, memory leaks have become quite recognizable as stats debugging tools like Grafana. I think of grocery stores and grocery carts and folks not returning their grocery carts to the cart return or taking the carts down trips down the block and down hills as computer memory. They have to be returned or eventually there's no more carts. Stack Overflows. One of the best developer help websites is named after one of the most profound errors in computer science. Stack overflows stem from a resource contention issue. Programs maintain a stack of priority ordered functions in their returns and a heap of arbitrarily allocated memory. And like memory leaks, if you issue too many functions calling themselves, this will exceed the stack and it overflows. These errors are unrecoverable. And in the Linux world, the killer will clean up all processes that exceed their stack. Programs that may exhibit these symptoms are often referred to as legacy code, and they cost a lot of money to be fucked about with. Async programming is required to make software that is partition tolerant and networked. And traditionally, the coordination of multiprocessing has been left to the operating systems, with thread schedulers responsible for tagging threads in and out of when they can execute. And each core of a CPU can execute a thread simultaneously and process as many threads sharing memory. And that sharing of memory requires the delicate and correct implementation of mutexes, critical paths, and semaphores to ensure that the executing code changes state intentionally and correctly. It is important to remember that an async operation may never return and it may never throw. Text messages to TCP packets to mail, async misuse means messages may never reach their final destination. Pointer mismanagement. Us web application programmers, we have it so lucky. We don't have to think about pointers or dereferencing. Modern languages might run in a virtual machine with managed memory or have a garbage collector available to deallocate or heap. But in C land, everything is either a value or a pointer to a value. And if you want to call a function with arguments, you pass those arguments by value or a reference of a pointer to those values. And this means consistency and careful management of pointers to arrays of characters, and countless bugs by thousands of programmers have been made this way for decades. And eventually, with the rise of Java and Ruby and other modern programming languages, the rule was clear. Primitives pass by value, and everything else will pass by reference. If you pass by value, it will be copied literally. If you pass by reference, it will be dereferenced, looked up. And consideration of whether to pass by value or pass by reference is something programmers stopped wanting to think about with regards to strings, which are so useful and prolific in programming, but require different strategies if you would intend to copy or mutate the words. Programmers want to manage strings, not pointers to character arrays, and this is why Rust has two kinds of strings: string and @stir. One allocates on the heap and is growable, the other lives on the stack and is static. Yeah, the mental overhead of two types of strings is initially jarring to beginner Rust programmers. But when the alternative is managing pointers, any abstraction is going to be better and easier to grok than that. And finally, we come to the bane of shared software defects, which is cache invalidation. And yes, this is the second of the two hard problems in computer science. Every programmer should recognize the comparative speed of their executing context. CPU registers are an order of magnitude faster than the L1 cache, which is an order of magnitude faster than the L2 and the L3 cache. And memory is faster than disk is faster than network speeds. The incredible speed of software execution is proportional to the capacity of its bandwidth and the price tag. The same goes for the execution environment. In software and in hardware, the caching of data increases the performance of retrieval by reducing the needs to access data from slower or distant storage mechanisms. Cache invalidation is the intentional changing of replicated data for accuracy's sake. When you want a Coca-Cola, do you go to the Coca-Cola factory and say to John Cola, CEO of Coca-Cola, "Hey, Slick, pass me a cold one, will you?" No, of course not. You're going to instead go to the grocery store. And the grocery store got it from a distribution center. The distribution center got it from the regional distribution center that got it from the factory. And Coca-Cola is a fine product that has done adequate testing and safety assurances to create a satisfying and sugary caffeinated beverage that is safe for humans, unlike a more dangerous and consumer food, such as, say, baby formula. The Bouncy Baby Formula company has the displeasure of having to recall their products. They must then invalidate the caches deeply of their entire logistics supply chain from the factory to the distribution centers to the grocery stores. And this is an unpleasant experience for any business, especially one that is susceptible to lawsuits from furious parents and governments and clients. But for a computer, cache invalidation means explicitly and correctly resetting and applying a new state, which is much easier, but it's still a challenge for two reasons. One, because cache invalidation is business logic. It is a work order, and it takes a process that surely takes new state and overrides the old state, and it does it right, and it does it right now. The correct implementation is always entirely custom, and it requires no mistakes. But two, changing state incorrectly can cause bugs of mutated state. Let me repeat that. Changing state incorrectly may cause bugs of mutated state. Any solution to cache invalidation is a step in both shared state tools and changing state tools. It means that a developer is susceptible to both domains of these bugs. And depending on how the cache is used and implemented, changes could be shared to other parts of the system. And if other parts of the code are not expecting unintentional or mistyped updates, it could lead to bugs of unstructured state. Cache invalidation is hard because its correct execution is entirely custom. It requires no mistakes, and done incorrectly, it could lead to all the domains of garbage, trash, software behavior. And so these are the bugs of shared state. Yeah, changing data is cool and reading unknown input is rad, but it's the copying of data and sharing it that has made computers really shine. And across networks, disk, memory, and registers, shared state means more than one source can read and sometimes write changes at a time, that the source of truth can quickly get lost. And when the data cannot be cleanly copied or shared, you get these symptoms of constrained and jumbled data. Multi-threading tools, parallelism, and a careless pursuit of HA and DR, and even the misuse of pointers in C can all cause these bugs. They tend to be hard to diagnose, trickier to address, and they require critical thinking to overcome. And that's the key thing here, critical thinking. These are needed to overcome shared state problems because humans can recognize the contradiction of an impossible dependency loop. And we might refer to this phenomenon as a catch-22, a noun coined by 20th century American author and badass Joseph Heller. Many young adults today trying to enter the workforce may experience this, denied jobs that require work experience that they cannot achieve without first getting a job. Catch-22s are paradoxical situations without natural solutions. They're cemented in logic and solvable only with determined human brains that can intervene in the solution and exit the cycle. These bugs occur when humans make mistakes. They have these symptoms and are caused by these errors when using these tools. Thank you. That's my presentation.